3.1 Capacitor and capacitance. What is capacitor? Capacitor can be defined as a device with one or more conductor pairs divided by an insulator called dielectric that is used to store electric charge. The dielectric can be made of paper, plastic, mica, ceramic, glass, a vacuum, or nearly any other non-conductive material. Have you ever wondered what inside a capacitor? If we look closely, we can see that capacitors have negative charge connection, positive charge connection, dielectric, metal plate, aluminium, and plastic insulation. So this is the outside part of capacitor. When a dielectric is used, the material between the parallel plate of the capacitor will polarize. The partner positive end of the capacitor will have an excess of negative charge. The partner negative end of the capacitor will have an excess of positive charge. This redistribution of charge in the dielectric will thus create an electric field opposite the field created by the capacitor. The net field created by the capacitor will be partially decreased, as will the potential difference across it by the dielectric. Besides, the dielectric prevents the plate of the capacitor from coming into direct contact, which will render the capacitor useless. If it has a high permittivity, it also increases the capacitance for any given voltage. There are many types of capacitor. Some of it are paper, electrolytic, polycarbonate, polyester, ceramic, and so on. Next is application of capacitor. First, capacitor in flash camera. The usual purpose is to briefly power high voltage flash tube used to illuminate a photographic subject or optically pump a laser rod. Number 2, capacitor in keyboard. When a key is pressed, it connects with capacitor pad and changes the capacitance at that specific point on the capacitor pad, which the keyboard identifies and registers as the exact keystroke. For capacitance C, it can be defined as the ability of a component or circuit to collect and store energy in the form of an electric charge. The SI unit of capacitance is farad, F. 1 farad equal to 1 coulomb over voltage. The capacitance value is dependent on first, dielectric material. The higher the dielectric key, the higher the capacitance. Number 2, area of the plate. The bigger the area, the higher the capacitance. Number 3, separation distance of the plate. The closer the plate are, the higher the capacitance. So this is the equation of capacitance. We can rearrange it to get what the question wants. Number 1, C equal to Q over V. C for capacitance of capacitor, Q charge stored in a capacitor, V voltage across capacitor. Number 2, C equal to K epsilon naught A over D. C capacitance of capacitor, K dielectric. Epsilon naught is permittivity of free space. The constant value is 8.85 times 10 the power of negative 12. A, area of plate, D, distance between plate. Example A. Calculate the capacitance of a parallel plate capacitor whose plates are 20 cm times 3 cm and are separated by 1 mm A gap. So A 20 cm times 3 cm convert to meter square and get 0.006 m square. D 1 mm convert to meter and get 0.001 meter. So K 1 because already mentioned A gap. So we use C equal to K epsilon naught A over D, and then we key in the value and get 53 picofarad. Question B. What is the charge on each plate if a 12V battery is connected across the two plates? So we use C equal to Q over V. The question wants charge on each plate, so we rearrange it and use Q equal to CV. We key in the value and get 6.36 times 10 to the power of negative 10C. Last question, what is the electric field between the plate? V equal to ED. The question wants electric field, so we use E equal to V over D. And lastly, we get 1.2 times 10 to the power of 4 V over M.
Then you are going to the next topic, which is 3.2 about the combination of capacitors. Combination of capacitor consists of two types of circuit, which is series circuit and parallel circuit. So I am going to explain about the series circuit. What is a series circuit? Series circuit is a one in which all circuit elements are arranged in a simple path. In a series circuit, the current through all elements is the same, but the voltage drop across each element is different. Then, how do we find the value of the capacitors in a series circuit? We can find its value by adding the reciprocal of individual capacitance, just like the formula right here, which is 1 over capacitance total equal to 1 over capacitance 1 plus 1 over capacitance 2 plus 1 over capacitance 3. So, based on the diagram below, we can see that there are 3 capacitance, which is C1 with 2 farad, C2 with 4 farad, and C3 with 6 farad. With the information given, we can substitute the value of each capacitance into the formula to get its value, which is going to be 1 over C1 to 3 equal to 1 over C1 plus 1 over C2 plus 1 over C3, which is 1 over 2F plus 1 over 4F plus 1 over 6F. The result will be the 1.09 farad. Other than that, when it comes to a series circuit, we can also find the voltage and charge using the formula below. To find voltage, we use V total equal to V1 plus V2 plus V3, and to find charge, we use Q total equal to Q1 equal to Q2 and equal to Q3. So looking back at the diagram, we can easily find the charge stored on the equivalent capacitor by using the formula of C equal to Q over V. To find charge, we arrange the formula into Q equal to CV, which will result into Q equal to 1.09 times 10, and the answer will be 10.9. As we all know that the charge on each capacitor are the same, so the answer will be Q1 to 3 equal to 10.9 coulomb. The diagram also shows its voltage, which is 10 volt. But how do they find that 10 volt? To find voltage across each capacitance plus to prove if the voltage is 10 volt, we will arrange the equation of C equal to Q over V to be V equal to Q over C. With that, we can substitute each value into the formula. Then, the voltage across for capacitor 1 is V1 equal to Q over C1, which is 10.9 over 2 equal to 5.45 volts. Then, the voltage across capacitor 2 is V2, which is Q over C2. The answer will be 10.9 over 4 equal to 2.73 volts. And the voltage across for capacitor T is V3 equal to Q over C3. The answer will be 10.9 over 6. The answer will be 1.82 volts. So, the total voltage in a series circuit is equal to the sum of all the individual added together, will be V total equal to V1 plus V2 plus V3, which is 5.45 volt plus 2.73 volt plus 1.82 volt equal to 10 volt, which is proof of the voltage given in the diagram. And that's how a series circuit should be calculated. But remember to always memorize the formula of capacitance, charge, and voltage, just like in the table below.
So my part is parallel circuit. So what is parallel circuit? Parallel circuit is one that has two or more paths for the electricity to flow. The loads are parallel to each other. Okay, next, when capacitors are connected in parallel, the potential difference across each capacitors is the same. The total potential difference across the circuit is V equal to V1 equal to V2 equal to V3. However, the charge on each capacitors are different. The total charge in the circuit is the sum up of charge on each capacitors, which means Q total equal to Q1 plus Q2 plus Q3. For parallel circuit, the equivalent in capacitance can be calculated by the formula C total equal to C1 plus C2 plus C3. Okay. Okay, next, like you guys see here, we have a circuit. So like you see, we have C1, C2 and C3 here. These three capacitors are connected in parallel. So you guys see that have a voltage here, which is a power supply. Let's see, the current move from positive here. So when you reach here, will separate into three ways, which is C1, C2 and C3. This type is connected being is called parallel circuit. So the capacitor connected in parallel. Okay, next. So we have example question for this chapter. So the circuit in figure 5 shows capacitors being connected across a 120 volt source. So we have a series and parallel circuit is combination capacitors, have a series and parallel. So we label 2 nanofarad C1, 3 nanofarad as a C2, 4 nanofarad as a C3. So calculate its equivalent capacitance. So we do the parallel first, which is C2 and C3. So C23 equal to C2 plus C3. This is parallel circuit. So they combine like this. So 3 nanofarad plus 4 nanofarad, we have 7 nanofarad. So the C23 is combined, the capacitor like this. So next we have to find a C1 to 3 we have to combine in one line. So C1 and C23 is series. So 1 over C1 to 3 equal to 1 over C1 plus 1 over C23. This is series circuit. So 1 over C1 to 3 equal to 1 over 2 nanofarad plus 1 over 7 nanofarad. 7 nanofarad it is which we were looking for earlier tadi lah. So the answer is C1 to 3 equal to 1.56 times 10 power of negative 9 farad. So the circuit, the capacitors become like this. C1 to 3 is combined and become a one line. Second question is the voltage across the 2 nanofarad capacitors. So we have a formula C equal to Q over V. We arrange the formula become Q equal to C times V. So Q123 equal to C123 times V123. So C123 is answer for the question 1. So 1.56 times 10 power of negative 9 times with 120 volt at the capacitors. So Q123 equal to 1.872 times 10 power of negative 7 C. So Q123 equal to Q1 equal to Q23 equal to 1.872 times 10 power negative 7 C. So C123 this is same Q. The question 2 want a voltage across the 2 and F capacitor, which is C1. C1 is 2 nanofarad. So we have a formula C equal to Q divide V. We arrange again the formula V equal to Q1 over divide C1. So Q1 we have no, which is 1.872 times 10 power of negative 7 divides with C1. C1 is 2 times 10 or 10 power of negative 9. So the answer is 93.6 voltage. So next we have a difference of series and parallel circuit formula. Series and parallel have a different formula. So for series, we want to find C. 1 over C total equal to 1 over C1 plus 1 over C2 plus 1 over C3. So parallel, C total equal to C1 plus C2 plus C3. So next for find a Q for series E, Q total equal to Q1 equal to Q2. For parallel, Q total equal to Q1 plus Q2. Next for voltage, we want to find voltage for series is V total equal to V1 plus V2. For parallel is V total equal to V1 equal to V2. So the formula with series and parallel is totally different. So you can have to remember the formula.
Next, I'm going to present electric energy storage.
to half CV square equal to half QV, where Q is charge, V is the potential difference, and C is the capacitance. The SI unit for energy stored is joule. Next, I'm going to explain about energy density. The energy per unit volume is the same no matter the origin of the electric field. The symbol for energy density is small u. The formula is U equal to half absolute naught E squared. The SI unit is joule per meter cube. The next one is some of an example for this subtopic. The first example is capacitance of a capacitor is 50 mF charged to a potential of 1000 volt. Calculate the energy stored in the capacitor. This question has given us V equal to 1000 volt and C equal to 50 mF equal to 50 times 10 power of negative 6 farad. We can use the formula for energy stored, which is U equal to half CV squared. After substituting the value, we can get the answer for energy stored U equal to 25 joule. Next example is find the energy density of a capacitor if its electric field E equal to 5V over M. This question has given us electric field E equal to 5V over M. And as we know, the value of absolute naught is 8.85 times 10 power of negative 12 F over M. We can use the formula U equal to half absolute naught E squared. After substituting the value, we can get the answer for energy density U equal to 1.10 times 10 power of negative 10 J over M cube.
So for the last subtopic, which is 3.4, dielectric. So what is dielectric? Dielectric in general can be described as a very poor conductor of electric currents. They are insulator and contain no free electrons. So basically, dielectric could be any non-conducting material or an insulator such as paper, glass, rubber, and so on. So, a non-conducting material is placed between the two metal pieces, making up a capacitor. So, why they are built that way? There are two reasons. As one, non-conducting material prevent the pieces from touching each other, which is important because if the pieces of metal were touching, no charge will ever get stored since you have completed the circuit. For the second one, it will increase the capacitance of the capacitor. So how does a dielectric increase the capacitance? For the first one, you can look at the diagram here. When you hook up a battery of voltage to a capacitor, the charge will get separated. So for the second one, if you remove the battery, the charge is stuck on the plate since the negative don't have a path in which to get back to the positive. So even if the battery is removed, the charge and the voltage among the plates will remain the same as the battery. Now, the dielectric is placed between the capacitor. Dielectric material are made up of atoms that consist of positive and negative charge. The negative charge in the dielectric are going to be attracted to the positive plate of the capacitor. Now, the close-up look of the capacitor. The negative charge in the dielectric are going to get attracted to the positive plate of the capacitor. But those negative can travel to the positive plate since this dielectric is a non-conducting material. However, the negative can shift or lean toward the positive plate. So this is when the polarization occurs. The atom kind of stretch and one end become overall negative and the other end become overall positive. Thus, when the dielectric is placed between the charged up capacitor plates, the attraction between the negative side or the polarized molecule and the positive plate of the capacitor causes the polarized molecule to rotate, allowing the negative to be a little bit closer to the positively charged capacitor plates. So back to the question, how does the dielectric increase the capacitance? If we take a look at the definition of capacitance, which C equal to Q over V, if we remove the battery, the capacitance is inversely proportional to voltage. When the charge remains the same and the voltage decreases, the capacitance is going to increase. So to answer the question, the dielectric reduces the voltage between the capacitor plates. Or you can also say that it increased the capacitance by lowering the voltage. It reduced the voltage because even though there are still just as many charges on the capacitor plate, their contribution to the voltage across the plate is partially cancelled. In other words, some of the positive charge on the capacitor plates are having their contribution to the voltage negated by the fact that there's a negative charge right next to them. What it means is that the positive charge at the capacitor plates react with the negative charge or the dielectric atom that sits right next to it. The same thing happened at the negative plate of the capacitor. So, the total charge on this capacitor has remained the same, but the voltage across the plates has been decreased because of the polarization of the dielectric. For us to know how much does the capacitance plate increase, we can use these two formula to calculate the new capacitance. We look at an example here. A parallel plate capacitor filled with a dielectric K equal to 4 is connected across a 250 volt source. The plate have area of 100 cm square and separated by a 10 mm dielectric. Calculate first its capacitance and second the new capacitance if the dielectric is removed. So for the first question, which is capacitance, the first thing we need to do is list out the information that the question has given to us. And here we have K equal to 4, A area equal to 100 cm square, which we need to convert to m square, and we got 0.01 m square. The third one is D distance, 10 mm, that we also need to convert to m, and we got 0.01 m. The fourth one is epsilon naught equal to 8.85 times 10 to the power of negative 12. We can use the formula that we have given just now, which is C equal to K epsilon naught A divided by D. Then we use the formula and insert all the information we have given just now. We have this just now, C equal to 4 times 8.85 times 10 to the power of negative 12 times 0.01 divided by 0.01. And the capacitance is 3.54 times 10 to the power of negative 11 farad. Second question, the new capacitance if the dielectric is removed. The formula is also given just now, which is C equal to K C naught. We can take our the capacitance that we just calculated just now, which is 3.54 times 10 to the power of negative 11 farad, and K4. Insert the information into the formula, and we got 3.54 times 10 to the power of negative 11 farad equal to 4 C naught, and our C naught is 8.85 times 10 to the power of negative 12 farad.